We are now recording and still looking for my first student. We'll go from current slide. And I'm sharing. Everything looks good except no students here. So I'm going to move my picture up here out of the way as much as I can. Okay. And get my pen set up. And still no students are here that I can tell, so let me know when you come in. Of course, no one's there to hear that, but if anyone's there, let me know. All right. I'll make any announcements after we get students here. Right now, we don't have any, so let's go on. We're in Chapter 4, Higher Order Differential Equations, and 4.1 is Preliminary Theory, Linear Equations. Okay? This preliminary theory part, first of every chapter, it seems like it goes on forever. And then you get to the real stuff, which is so much fun, and those are really short and they get by too fast. Okay, so let's do example 8. We haven't learned how to do these things yet. They're still giving us sort of, well, if you got it, here's what it is. So here's a function, and I don't like these functions very well. Y is equal to, oh, Keiston's here. Welcome. Good to see you. Hey. Whoops, I started to put you in the wrong place. I can't get my pen to write now. Okay. All right. You don't happen to can tell if Vincent is also here, can you?
I don't see.
Yeah. I only see one, sometimes two at a time, but last class I could only see one block at a time. Sometimes I'd see the person, sometimes I'd just see their name. In fact, last class I never saw a person, all I saw were their names. This time I can see you, okay?
I think it gives you an option to either share the video or not.
Yeah, well, I'm sharing. But you see, I've got so many things open. I've got Screencast-O-Matic open, I've got PowerPoint open, and I've got Zoom open. And I think it just limits what this little old computer can do. So anyway, we'll just go from here. First, okay, I wanted to ask you a question too. Do you have a device that shows message as well as announcements on Blackboard? What kind of device are you using?
Right now?
Yeah.
Laptop.
Okay, a laptop, as in a Microsoft type environment. Okay, not an iPad. I had a student in this morning's class who had an iPad and he could not access messages. So therefore, if I just sent out something by message, he never saw it. And I didn't know that, okay? So from now on, I'm going to only make, this sounds redundant, my announcements via announcements, okay? I started off doing that because that's how we used to do it in the old Blackboard. But then I found this little icon over here that said messages. And I thought, oh, that's a shortcut, so I don't have to go through all the steps to get to an announcement. So I started using that because when I was posting something there, I went through the same steps as I did through an announcement, so I thought it was an announcement. Okay? Well, I found out yesterday that those are two different things, okay? Or maybe it was the day before. So I started doing both, and then this one student this morning, he couldn't even do the messaging at all. He can't send me a message, he can't receive a message. And I think it's because it's an iPad. So I'm going to send everything I do through announcements from now on so everyone can get it. And I'll check messages every day just in case any student has sent me anything back. Now, I also put out there a bunch of things that the dean and other people have sent. I guess I'm going to have to copy those over to announcements as well, because obviously some people aren't seeing them, so or can't see them. So anyway, I just wanted to find that out. Are you aware of all the changes that have occurred since the weekend? For instance, we're not going back to campus next week. Did you know that? Okay. Did you also, and you may not care about this, but did you also know we're not going back to campus in the summer? Our entire summer schedule is going to be courses just like this. We're calling them virtual courses, virtual classrooms. Just like we're in a class, only we're not. We're in our homes. There will be a few online classes. We always offer some online classes for people who didn't live anywhere in the area. But now students can be in either virtual classes that way, or more of the online situation would be if a person, say, works during the day and their awake time is at night. Okay, well, we don't offer any classes late at night, so that's where an online class would be very beneficial. Or people whose schedule change, like they might be working a shift for a month and then a different shift for another month, so they could take classes at one time the first month but couldn't take them the second month. Well, an online class would be ideal for that. But these are going to be, the virtual classes are going to meet at regular times, just like we're doing now. The instructor's here, the students are there. Okay, so we're going to do that in the summer too. No decision has been made about fall yet. Everyone's hoping we'll be back on campus. I don't know if we will or not. It's hard to say, because you see, what I've been basing all my guesses on, well, my wife is really good at this because she's an epidemiologist, infectious disease epidemiologist, and she's been studying the other countries where the infections started sooner than they did us. So we can look back and see what happened with them. What's happening to them now will probably be happening with us a month from now. And we see some of these countries, like China, apparently has peaked and the infections are going down. They've opened back up, I think, every place in China. Italy, I think the infections peaked. Their death rate, I don't know if it's peaked yet, but they were a little behind China. Well, we are following almost exactly the same track that Italy did. We may not have quite as high a death rate as they were having, because where it hit in Italy was where a lot of retired people lived, and that hit them pretty hard, I think. So here, our retirement centers were not the first place hit, so they've been able to, contain a little bit. In Washington State, some of the retirement centers was where it hit first, and they had a lot of problems there. So anyway, it's hard to tell. The other places aren't far enough ahead for us to tell what summer is going to do yet, but it's looking a little promising. But on the other hand, there's just so much we don't know about this virus. China may turn around and have a secondary wave. And if they do, then we're all in trouble, because we're probably all going to follow the same suit. So anyway, we'll see when we get there. Some of the other viruses typically sort of die off a little bit in the summertime, but then the next fall they may come back with a vengeance. So we're going to have to just wait and see. All right, that's all I know, all the news. Oh, here's the other thing. Just about every service we offered on campus before, we are still offering now. It's just in a virtual environment. You can contact the records office by just emailing records@lawsonstate.edu. You can contact the business office by doing business office. They put both words in there. Business office, no spaces, no dashes, nothing else. Just business office at lawsonstate.edu. So any office you want to locate, you send the message like that. Someone is monitoring that at all times, either from home or from campus. Some of them have to go to campus every now and then just to take care of things you can't do at home. So there will be someone who can answer just about any time, not day or night, but any time during most normal hours that the college would normally be open, you'll be able to get responses. We're doing advising that way. We're doing registration, strictly online registration. So anything that you need to know. Were you planning to do any courses this summer with Lawson?
No, sir. I don't. There's not any classes that Lawson offers that will be.
Yeah, I figured you were about as high along in math as you were going to do. I didn't know if there were any other disciplines you were going to do. Okay, well then that may not matter to you much, but I just wanted to let you know, let people know we're still open for business in the summer. We're just not on campus in the summer. All right, so let me go back. I was just about to do, we're in Chapter 4, Higher Order Differential Equations. We're in 4.1, Preliminary Theory, Linear Equations, and we're in 4.1.2, which the title of that one was Homogeneous or Homogeneous Equations. It's a very long subsection, as long as most sections are. But we're almost through with that. Here was example 8, the top, I'm getting afternoon, I lose some of my sun, so I'm going to turn on the light here. It may make the reflection too great. Is that okay?
That's good.
Okay. Here's a function, and one I don't particularly care for. Y is equal to 4, this is on page 127, 4 times the hyperbolic sine of 3x, oops, well that's correct, but I didn't mean to put that big a space between those. Sometimes my pen is slow, and I've gotten used to hesitating, but it's writing very well right now, knock on wood. Now one thing that's not happening, my power light is not good. I have a bad connection between my plug and the computer, and it'll be perfectly fine, and then as the computer heats up, I guess the contact is not as good, and I cannot get the light to come on. And I worry about this because my battery is so weak, because this has happened before. It runs down the battery, and this may be a little bizarre here. I'm going to drape it over the top and see if I can. Well, I can't get the light to come on at all. Well, it is. It's very faint. Okay. Hopefully that'll last us. Okay. Y is equal to 4 sine 3x minus 5 e to the minus 3x. Now, they claim that is a solution to this differential equation. In example 7. Okay. Oh, okay. The one in example 7 was y double prime minus 9y is equal to 0. A linear, second order, homogeneous differential equation. Now the solution we came up with there, we did last time, was y is equal to c1 e to the 3x, and my pen is not writing well at all. That's why I checked my light before, because it seems like sometimes those go together and I don't know why. C2 e to the minus 3x. Okay. Now how can both of those be solutions to the same differential equation? I thought at some time in the past it said if you have the general equation, they should be the same. Well, they don't look anything like each other except for the fact you have an e to the minus 3x in both of them. Well, here's why I don't like the hyperbolic sign. it's sort of like someone just made up another name for something that was pretty simple to begin with. And here's what I mean. A hyperbolic sign, and I don't know if this is anywhere in your book or not. Did you do these in calculus, the hyperbolics? And
Yeah. I
you
mean,
did.
as
Okay.
far as like differentiating and integrating.
What's that?
Talking about as far as like differentiating and integrating them.
Yeah. Well, the thing is, in my mind, they're almost ridiculous to even have, because, and frankly, it's mostly because I'm not a memorizer. And you almost have to memorize. They're enough like a sine and a cosine that they're sort of similar but very different. Okay, and that makes it harder to remember. So here's what a hyperbolic sine, and I'll use the same thing they have, of 3x. Well, no, let me just do a general case. Hyperbolic sine of u. Okay, whoops, that's not what I wanted. Yeah, it is. Okay, hyperbolic sine of u is defined to be e to the u minus e to the minus u over 2. That's what a hyperbolic sine is. Okay? So therefore what we have here is 4 times e to the 3x minus e to the minus 3x over 2 minus 5e to the minus 3x. Okay? That's what our function up there is. Well, let's see what happens to this. If 2 will go in the 4 twice, right? So that gives us 2e to the 3x minus 2e to the minus 3x minus 5e to the minus 3x. Doesn't look like it's coming. Oh, yeah. Well, what is that? 2e to the 3x minus 7e to the minus 3x. Well, guess what? That's exactly like this form here. It's just C1 is equal to 2 and C2 is equal to minus 7. Okay? So sure, that is a solution because, I mean, the only thing they did to mess it up is put that hyperbolic sign in, and if you just put the definition of hyperbolic sign in, you get the same form. So to me, I don't know what they were trying to show in that problem, but indeed, that's what you got. And that's kind of what they did. They went sort of around their elbow to get to the ear to do it, but that's all really you have to do. Any questions on that one?
Yes.
Okay. Let's go on to example 9. Okay. Here's a function, some functions. Y sub 1 is equal to e to the x. Y sub 2 is equal to e to the 2x. And y sub 3 is equal to e to the 3x. Very cleverly named. Okay. They claim that these three functions satisfy the third order differential equation y triple prime, third order, minus 6y double prime plus 11y prime minus 6y equals 0. Homogeneous or homogeneous differential equation. Okay? Now, you got three equations. They satisfy a third order differential equation. Does that mean these three, I'm trying to remember the term they use for it, fundamental set? Do these form a fundamental set for that equation? Well, they have to be solutions, and they say verify that, I think. Did they? No, they didn't. That was in the earlier problem. They didn't say verify. It wouldn't be too hard to verify. E to the x, the third derivative of that is e to the x. First, second derivative is e to the x. First derivative is e to the x, and y is e to the x. So basically, if you just add your coefficients down, you should get 0. 1 minus 6 is minus 5, plus 11 would be plus 6 minus 6 is 0. Yeah, that one worked. That one's easy. Now, for the next, they're a little bit more difficult. If y is e to the 2x, y prime would be 2e to the 2x. Y double prime would be 4e to the 2x, and y triple prime would be 6e to the 2x. So let's see what we get here. 6e to the 2x minus, what did I say that was? 4. 6 times 4 would be 24e to the 2x. The 2x's aren't going to bother us any. Plus 22e to the 2x minus 6e to the 2x. Is that equal to 0? Well, let's see. Add the positives together, and you get 28. Whoa. No, I'm sorry. I messed up there. Y triple prime is 8, not 6. Okay. I can't multiply. I was adding. Okay. 8e to the 2x. And 8 plus 22 is positive 30. Minus 24 minus 6 is minus 30. Those add. Okay. So that one did. All right. Let's do the next one. Now I'm going to be really lazy here. Oops, I should have left that one the same. Okay. Y triple prime. If y is equal to e to the 3x, y prime is 3e to the 3x, y double prime is 9e to the 3x, and y triple prime is 27e to the 3x. Minus 6 times 9, that's minus 54e to the 3x. And y prime would be, that's 11 times 3 would be 33e to the 3x. And then that would just be a 6, minus 6. So let's add our positives together. You get 60. Add your negatives together. You get 60s. Yep. All three of those are solutions. Now, that doesn't mean everything to us. It's important. They all three are solutions. But for them to be a fundamental set, they have to be also linearly independent. Now, how do we check linear independence? You weren't here last time, but I think we did the Wronskian.
Oh, yeah.
Okay, and the Wronskian, huh?
I was thinking of
Okay.
like the initial way they define like a linearly dependent. So
Right.
like basically they all have to add up to 0.
Okay. What this is going to produce is a 3 by 3 matrix. Okay. The top row of that matrix are those three functions: e to the x, e to the 2x, and e to the 3x. Second row will be the first derivatives of those functions, which would be e to the x. You tell me the next one.
2e to the 2x and 3e to the 3x.
The next one will be 3e to the 3x. And the third row will be the second derivatives of those functions: e to the x, 4e to the 2x, and 9e to the 3x. Now, that looks like a mess to take a determinant of. Unless, of course, you use the fact that it's a 3 by 3, so we can just repeat the first two columns. E to the x, e to the x, and e to the x, e to the 2x, e to the 2x, I'm sorry, 2e to the 2x, and 4e to the 2x. Okay? Now, that's not really a determinant, but I'm just saying this is how we're doing it. Remember what we do next? Do your down diagonal, and that would be 18. 2 times 9 is 18. And then multiply those e's together, and you get e to the 6x. Because when you're multiplying same base, different exponents, excuse me, I've got the hiccups now. Different exponents, keep the base, add the exponents. Okay? Going down the other way, the next main diagonal there, you get 3 plus 3 e to the 6x. And the third diagonal is a plus 4 e to the 6x. Okay. Now, I'm going to erase my construction lines there because they just get in the way. Ooh, I thought I was going to erase them. Okay. They just kind of get in the way. All right. Now we do the up diagonals. But on up diagonals, you subtract them. So there's a minus 2e to the 6x, a minus 12e to the 6x, and a minus 9e to the 6x. Okay? Adding those numerators together, adding the top row together, the positives together, you get 22 and 3 is 25e to the 6x, minus 12 and 11 are 23. So that gives you 2e to the 2x. 6x, I'm sorry. And I see Vince's iPhone came on. So Vince is here. Perfect attendance today. Way to go, team. All right. Vince, we're doing example 9 on the top of page 127. We're kind of in the middle of that. We've just about done what you see in the book. We've just determined, okay, let me fill you in. They told us these three functions were solutions for this third order differential equation. 3 solutions, 3. We're hoping that forms a fundamental set. But it doesn't necessarily. You can have 3 solutions that are not fundamental set. To be a fundamental set, of course they have to be solutions. We did verify they were solutions earlier. But the other thing, they have to be linearly independent. So that's what we're doing with our determinant here that we've expanded. It was a 3 by 3, and we expanded, copied over the first 2 columns, and then did our diagonals like you're supposed to, and we found out that when you sum all those together, you get 2e to the 6x, which is not and never will be, never can be, 0. So therefore, the Wronskian is not 0. That means this particular set of functions are linearly independent of each other. So that tells us that the general solution for that differential equation, since these are 3 solutions and it's a third order differential equation, and these 3 solutions are all linearly independent, that we can conclude that the general solution y is equal to some linear combination of those 3 solutions. So C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. That has to be your general solution for that third order homogeneous linear differential equation. Homogeneous because, or homogeneous because that is equal to 0. That's what makes it homogeneous or homogeneous. Okay. Now, I haven't seen if Peyton, I said we had perfect attendance. Peyton said he came to pick up his materials that Monday before we closed, and he was going to try to get back in the course. He had paid for the course, but because he had never shown up for the course, they removed him from the course. Well, he was going to see if he could reverse that, and then everything closed. So I don't know if he ever made it. So if either one of you hear from him, anything, let me know. So far, he's not showing back up on the roll sheet, which means he didn't make it back in, but they may be delayed because of all this closure. So anyway, from what I know now, it's perfect attendance. Not that that matters. Okay, so we found the general solution just like they suggested in the book. Y is equals C1 e to the x plus C2 e to the 2x plus C3 e to the 3x. Now, it's just happenstance they gave us one that these were the solutions for. There is no connection between these 1, 2s, and 3s and those 1, 2, and 3. You could have written those in any other order. You could have said C3 e to the x plus C1 e to the 2x plus C2 e to the 3x. That would have been just as general of a solution because those are arbitrary coefficients. Just happens to be in this case it was. We are finally through with 4.1.2. Thank goodness. Ready to go to non-homogeneous or homogeneous equations. Any objections? Any questions on 4.1.2? All right. Let's clear the screen then and get going on 4.1.3. Non-homogeneous or homogeneous equations. Any function y sub p, now we're going to introduce another kind of function, y sub p, okay, that is free of arbitrary parameters okay, but also satisfies the equation the differential equation. Now this is not the same differential equation we've been looking at. The ones we've been looking at have all been homogeneous. Now, however, we get one that the equation is not equal to 0. Is equal to some other function. I think they usually call it g of x, isn't it? Well, they don't even list it here, but we'll just say g of x. Now, just a quick reminder, that g of x may just be a number. I think the first one they have here is a 27 or a 3 or something like that. It's not 0, though. That's the key. The homogeneous differential equations, whatever your y terms had, those are all your functions, and all the derivatives of the functions, linear, nth order differential equation, but it was equal to 0. Now we're going to deal with one looking just like that on the left, but on the right it's not going to be 0, it's going to be some other function. Could be a constant function, or it could be a function of x. Guess what? There can't be any y's in it, or y primes, or any other y's. Only x's over there, or constants. Okay? You can have all sorts of functions over there, but that. Now, so yp, free of those arbitrary parameters, like your C1, C2, and C3, they don't have those, but they still satisfies the equation. Here's one for instance. Y sub p, we call it a particular solution. That's what the P stands for. You We hit it earlier. Yeah, and they mentioned it here too. Particular solution. And they say that here. That is a particular solution. What that means, it's not one of the arbitrary or have an arbitrary coefficient, but it has a particular solution with no coefficients. Okay? And they're saying here, here's one, y sub p is equal to 3. Now that's a pretty simple particular solution. Well, here is the non-homogeneous equation. Y double prime plus 9y is equal to 27. Not homogeneous anymore, okay? Now, we're only worried about how you satisfy that 27. Remember when we did the other things with the arbitrary coefficients, those other solutions, the independent solutions, they were all making it equal to 0. Well, the particular solution makes it equal to 27. Well, if you do y sub p prime, what is the first derivative of 3? 0. Okay? What's the second derivative of y of 3? Or that's also 0, because the first derivative of 0 is 0. Well, sure enough, if we plug in 0 plus 9 times 3, look at that, that's 27. Now that's a particular solution. You don't have any arbitrary coefficients. 3 is not arbitrary. It is the solution, okay? It's not that's an arbitrary constant. No, 3 is the solution. Okay. Now, let's extend this to be a little more general and, frankly, a little more complicated as well, unfortunately. Okay? What if you have y1, y2, y3, ... up to y sub k, and these are solutions of your homogeneous case. Okay? I'm just going to abbreviate it that way. On some interval I, okay, and y sub p is any particular solution to the non-homogeneous case. Okay, the non-homogeneous case on that same interval I. Okay, here's what the conclusion is. These are solutions for the homogeneous case, so just like we did before, a homogeneous case, your general solution, y, is going to be some linear combination of them, c1, y sub 1, plus c2, y sub 2, plus c3, y sub 3, plus ... plus c sub k, y sub k. Okay? Your general solution for the non-homogeneous case is going to start out the same way it did for the homogeneous case, except now we just add, with no c's attached, y sub p. Okay? Because y sub p is a solution, a particular solution. It doesn't have an arbitrary coefficient. That will then make, because you see what? If you plug all those into your same differential equation on the left, you know that's going to come out being 0, and then what's on the right is going to be your y sub p. Okay? Well, when you do all the derivatives and stuff like that. Okay? So this is a solution of the non-homogeneous or homogeneous equation, whatever that linear nth order differential equation was. Okay, now that leads to theorem 4.1.6, which is basically the same thing we just said, though they phrase it a bit more mathematically perhaps. So I'm going to erase because it's sort of a big theorem. I'm afraid I'll run out of room. Okay, so what they say here is let y sub p be a particular solution of the non-homogeneous linear nth order differential equation, on an interval I. And let, before they put these from front, now they're putting them behind, y sub 1, y sub 2, y sub 3, ... Now they're using y sub n. I don't know why they randomly changed their, well, they did this because they called it an nth order differential equation. Okay, that's why. And this, they say, is not just a set of solutions, but a fundamental set of solutions. Of the associated homogeneous differential equation. On that same interval I. That's what's given. Now this is pretty straightforward, but just to get what it is, P doesn't have a very long tail, does it? You have a differential equation. The left-hand side is all linear nth order differential equation. Now leave off something. And if that's equal to 0, that is your homogeneous case. But this one isn't equal to 0. It's equal to something, some function of x. Could be a constant function or any other function of x. Any other function of x. Now, if this group here, your y sub p is a particular solution of that non-homogeneous case that has that function at the end, something on the right-hand side. It is a particular solution. If you ignored that on the right-hand side and made it a 0, then your y1 through yn are not just n solutions, they're a fundamental set of solutions of the homogeneous case or homogeneous case. So that's what we have. These are the solutions. If you set the left-hand side equal to 0, this is a particular solution if that right-hand side is not equal to 0. So, if that is a setup, then here's the conclusion. Then the general solution of the equation, the differential equation, on that interval is y is equal to c1, y1, and they're putting their of x's in here, which is harder to write, plus c2, y2 of x, plus c3, y3 of x, plus ... plus c sub n, y sub n of x. That covers your homogeneous solution. That covers your fundamental set. It covers everything. You're in arbitrary parameters. But here, what you do is add the y sub p. Not another coefficient, that y sub p, which was a particular solution of the non-homogeneous case. Okay? And then the i's here are, they made it pretty obvious. The c sub I, when I is equal to 1, 2, 1, 2, 3, dot, 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 all the way up to n. Made it pretty obvious, I thought, that they put that in. And these are arbitrary coefficients. Okay, arbitrary coefficients. Now, they do a little proof here. It's a pretty straightforward and general proof. And please pay attention to it. I mean, no big deal. Now, here's a few more words. We're going to be using these words a lot in the subsequent sections. In fact, a whole lot, okay? So I'm going to, well, let's see. I guess I can define it here. Okay. It says, you see in that theorem we just wrote there, that the general solution of the non-homogeneous linear differential equation consists of a sum of two factors. Okay? Here's the first group, all of those. Okay? And then the second group are your particular solutions. We only had one here. You may have more than one. Okay? Now, what we call this, these here, we call the characteristic solutions. We don't call it general anymore. It was a general solution for your homogeneous case, but it's no longer a homogeneous system. It's a non-homogeneous case. So this is now called the characteristic solution. I hope I'm saying that right. No, it's called the complementary function. Okay. Y sub c, that's what we call the complementary function. Okay, it's the sum of all those parameterized equations, the complementary one. It has the c's in it. That's why they call it y sub c. It means complementary. And, of course, the other one is called the particular solution, which we said at the very beginning. Okay? Now, so, in other words, to solve a non-homogeneous linear differential equation, you first solve the associated homogeneous case. That's the thing where you set the right-hand side equal to 0, all the terms with the y's in them on the left-hand side, all without the y's are on the right-hand side, and that's the complementary function is the sum of the homogeneous case. Okay? And then, and we haven't learned how yet, find any particular solution for the non-homogeneous case. Okay? That's what we'll be focusing on next. So the general solution then, the general solution is your complementary function. That's this part, y sub c, plus any particular solution. Okay, and you can have several of them. So this is basically y sub c plus y sub p. Okay. Now they've said that about 3 or 4 different times in almost the same way, so I think they're trying to make a point. All right, to erase?
Yeah, we good.
What's that?
I was saying yes.
Okay, I'm glad you did because I just erased it. Okay, I didn't hear you till I had already hit the button. So they tell us here, here's a particular solution. Again, they're not telling you how they get these. That's coming next in later sections. Not now. We're only doing this, whatever they call it, preliminary theory. It's a really weird seeming one. Minus 11/12 minus 1/2 x. Now they say it's readily shown to be a particular solution for this non-homogeneous differential equation. Y triple prime minus 6 y double prime plus 11 y prime minus 6y is equal to 3x. Now, that wasn't the one we had before. It looked awfully close to that. I know I saw it. Where was that? Goodness gracious. Oh, there it is. That is the one we did in example 9. Okay? It's exactly the one we did just a few minutes ago in example 9. Okay? The left-hand side is, when it's equal to 0. Okay, to write the general solution of that, we must be able to solve the associated homogeneous differential equation. We just have. Okay, that's a triple prime there. Okay. Example 9, we saw that. The complementary solution, y sub p, we were calling general solution for because that was a homogeneous case, but we set that equals 0, and now we call that a complementary solution. That's c1 e to the x plus c2 e to the 2x plus c3 e to the 3x. Go back and look, and that's exactly what we got. Okay? Now, they say it's readily shown. We haven't readily shown it. Let's do so. Let's take the first derivative of that, y prime of your particular solution. What would that be? Negative 1/2, that's all. What's your y double prime of that particular solution? 0. And that's also y triple prime of that particular solution. Because once you got a constant, all the subsequent derivatives are 0. Okay? Well, now let's take those values and plug them in here and see what we get. We get 0 minus 6 times 0 plus 11 times minus 1/2 minus 6 times minus 11/12 minus 1/2 x. Supposedly that's equal to 3x. We need to make sure it is. 11 times negative 1/2 would be minus 11/2. Agreed? Okay. Minus 6 times minus 11/2 would be plus, well, the 6 will go into 12 2 times. That would be plus 11/2. Ooh. Minus, no, plus half of 6 would be 3 plus 3x. Sure enough, that's equal to 3x because these two add to 0. Wait. I wrote down something wrong. It's 11/12. Yeah, this was halves. I wrote a 12 and it should have been a half, right? Because I did 6 into 12 was 2, and that would give you positive 11 halves. I wrote down 11 twelfths. Yeah, so that adds to 0. That gives you that. So yeah, it was pretty easy to show if you didn't write down the wrong number. Okay, so we have a complementary solution. We've just shown that a particular solution works. So what's the general solution? Y is equal to the complementary solution, C1e to the x plus C2e to the 2x plus C3e to the 3x. Then you write down your particular solution, minus 11 twelfths minus 1/2 x. There's your general solution that solves that differential equation with a 3x there rather than a 0. All right. And that's the solution they got as well. C1e to the x plus C2e to the 2x plus C3e to the 3x minus 11 twelfths minus 1/2 x. Done. All right. Didn't you love superposition principles? Here we got another one, this one for non-homogeneous equations. Okay? And I think I'm going to need more room. Vince, did you have a question? Your phone popped up.
No, I just lost connection for a second.
You just what?
I lost connection for a second.
Oh, okay. All right. So let me clear my screen. Okay. And here's theorem 4.1.7. What if you have a bunch of particular solutions? Y sub P1, Y sub P2, you got subscript of a subscript here, Y sub P sub 3, all the way up to Y sub P sub K. That's another subscript of a subscript. These are K particular solutions. They're all K of them are particular solutions of the non-homogeneous linear, goodness gracious, nth order differential equation, and it's a non-homogeneous, so there's something on the right hand side, maybe a whole bunch of somethings to have that many particular solutions, okay, on some interval I, corresponding in turn to K distinct functions. That would be G1, G2, these are all functions of x, G3, dot, 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 up to G sub K. Here's what they're getting at. You have these distinct functions, the G's, and every one of them has its own particular solution, okay, for those Y's that you have there. Those are the solution for these in turn. So what they mean by that is Y sub P sub I denotes particular solution for G sub 1 of x. Okay? So in other words, g sub I. Okay? So one of these here, one of these in here, goes with each one of those down there. Okay? When you plug the whole differential equation in there, but equal to just that one. So I is going from 1 to k. I don't know why they put that. I equal 1, 2, 3, dot, 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 up to k. Pretty obviously, that's what it means. Okay? Now, if that's the case, then your overall particular solution for this sum of all these g sub k's here, when you add them all together, the y sub p of x is going to be your superposition. Y sub p1 of x plus y sub p sub 2 of x plus y sub p sub 3 of x plus dot 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 plus y sub p, and this is k, sub k of x. Okay? And that is a particular solution when you had all these added together on your right-hand side. Because each one of those had a particular solution. Each one did. So if that's on the right-hand side, those added together, you just take the particular solutions and add them together with no arbitrary coefficients, just the sum. Okay. And they go through and have a little proof of that. And I think it's a pretty straightforward proof, but I'll let you look at that yourself. Now again, here we go. They give us the answer and say, show that it worked. Not show that it works, but verify. I don't know what we're saying. Yeah, you should verify. Here is a y sub p sub 1. A particular solution of minus 4x squared. They claim this is a particular solution of this. Y double prime minus 3y prime plus 4y, I left off the 4y is equal to minus 16x squared plus 24x minus 8. That seems pretty incredible that one little particular solution would work out to be that fairly complicated form. Now, I could almost hear you yelling, not quite, almost hear you yelling when it said, trying to find when to express that word here. Distinct functions, G1, G2, and G3 up to G sub k. Now wait a minute. Aren't these three distinct functions rather than one function? No, that is a polynomial function. So don't split up a polynomial function when we're doing this. We're not getting there to do them yet, but that is a single polynomial function. It will have one particular solution. Surprisingly, it's a single term polynomial. Okay? Now, y sub p sub 2 is e to the 2x. And that's a particular solution of the same left-hand side, but now that's equal to 2e to the 2x. Okay? Now that looks a lot more reasonable in some sense, but that's a, what was the term for it? A distinct function of x. Okay, a distinct g function of x. Okay, so, and Those look pretty reasonable. But guess what? We have another one, y sub p sub 3, and this is x e to the x. Okay, and that's a particular solution of the same left-hand side, but this time it's equal to 2x e to the x minus e to the x. Okay, and again, I can almost hear you scream and say, wait a minute, is that a distinct or is that two distinct? That's one distinct because they're both to the x. This is to the 2x. That can't be included in this, but these can. Okay? Distinct solution. I mean, distinct equation, function on the right-hand side. Okay. Now, if that's indeed true, that these are all solutions to the same, whoa, goodness gracious, I didn't know that did that. Okay, it's out of sight and out of mind. This same thing here, this left-hand side is the same, for some reason my pen's not writing, okay. So left-hand side is the same on all three of these, and yet we have a separate particular solutions for this. So the superposition principle says that then the if you had your original equation, well, no, they say it, they always put the answer, not always, sometimes they put the answer first, okay? So this is claiming your, I wish they didn't put y. This should be y sub p, the general particular solution, okay? Y sub p would then be the sum of these, y sub p sub 1 plus y sub p sub 2, my pen's not writing, plus y sub p sub 3. Okay? That would be your particular solution for the differential equation y double prime minus 3y prime plus 4y is equal to all of these. Now, I'm going to put them in parentheses. No, they don't, so I won't. Minus 16x squared. There is a minus on there. I said it, but it wouldn't write. Plus 24x minus 8 plus 2e to the 2x plus 2x e to the x minus e to the x. Okay? So what we have here, we haven't said anything about the complementary solution. Nothing at all about it. We'll get to that later. But for this differential equation, with this as the right-hand side on the non-homogeneous side, and these being the particular solutions for this equation, that equation, and these two grouped together, unique functions, then this is a particular solution for that situation. Particular solution, saying nothing about the complementary, complementary solution. Okay. And what they do, rather than putting parentheses around them, they call this G1 of x, they call this G2 of x, they call this G3 of x. So you add the three particular solutions together in a superposition type of way. Okay. Now, if these p sub i's are particular solutions of your G sub i's, which we assumed they were, those being our G sub i's down there. Then the linear combination, now we start putting parameters in, because they don't have to just be the sum of those three. It can be any linear combination of the sum of those. So that's why they left off the P before, because the real P, I didn't like them just saying P, Y, because that indicates general, would be C1, Y sub P sub 1 plus C2, Y sub P sub 2 plus C3, Y sub P sub 3. Okay? That is now your general fluid. Oh wait, I'm sorry. That's not what this is saying here. When the right-hand side, this is what was confusing, because they said no arbitrary coefficients, but what if you had a C1 here, a C2 here, and a C3 here? I wish I'd have called these something other than C's, because that's what we're used to seeing in the complementary solutions. Why didn't they use a different letter, D or something like that? Then that would have made more sense. This makes you think these are arbitrary coefficients. They're not. They are the coefficients that showed up here, here, and here. Multiplying by those. For instance, I can't back off and do it, but if this would have been a 14 here, then the C2 would have been a 7, because this is a particular solution here for this being a 2 there. Okay, so have to sort of keep up with what's there. These are not arbitrary coefficients making a linear combination. These are the coefficients that showed up here around these functions, if these functions just happen to have coefficients around them. So it says now, before we actually start, let's see, how are we doing on time? Are we almost there? About 3 minutes? Okay. Let's see if we can get there. Before we actually start solving homogeneous and non-homogeneous linear differential equations, we need one additional bit of theory, which is presented in the next section, and that's going to be section 4.2. Let's just quickly go over these remarks. First, we've been talking about linear systems, okay? When you have a non-homogeneous differential equation, but it's all a linear, that's called the linear, nth order linear system, okay? The n time-dependent variable functions here, okay, this is with when t is your parameter and it's time, okay? When you're dealing with time as the independent variable. These are called the state variables of the system. These, your y of t, your y prime of t, your y state variables. At some, recall that at some time, these give the state of the system at that time. Okay, that's why they call them the state variables. The function g on the right-hand side is called the input function or the forcing function. This is the one that makes it do something differently. Okay, and the solution y of t of the differential equation is said to be the output or response function from that input for that situation. Now those are all just terminology you don't really need, but they're trying to tie it into when you get to upper level courses and need these things, you'll run into those terms. So I just wanted to mention them. Homework exercises here. 4.1.1. Again, I've given these before, either 1 or 3, whichever are in the back of the book. 5 or 7 if they're in the back of the book. 9 if it's in the back of the book. 11 if it's in the back of the book. 13 if it's in the back of the book. That's 4.1.1. 4.1.2, any of the odds 15 to 21, if those that are in the back of the book. Any of the odds 23 to 29 that are in the back of the book. And then the new ones that we hit today, 4.1.3, the non-homogeneous equations, either 31 or 33 if they're in the back, 35 if it's in the back. And that's the only new ones we picked up. Now, most of these discussion problems are not in the back, but if you find any that are, you can do those as well. And we will pick up with reduction of order that last little bit of theory that we need, they say, in 4.2. And this is a very short section. Hopefully we will finish it and move along next time. Any questions? Okay. Have a good, safe weekend. You got plenty of homework exercises you can play with. Keep yourself busy. Also, I think there's a couple of research papers that I don't have yet. You can work on those. And we will be back here on Monday. Have a good weekend. All right, I'm going to stop the share here. And I'll end the meeting for all of us. And we'll see you next week.